So Marco was a graduate student here, and he graduated a couple years ago. And he went to Caltech. Marco worked on measuring the lots of stuff, including measuring the power spectrum of the cosmic infrared background using glass. And so when he did it, he was the first one to do it. And then he worked on measuring the cosmic infrared background in CMB experiments we put together. And so he measured the ACT and glass CIB contamination. And then he moved on to Caltech and started actually working on his own survey that is called Herschel. And that's what he's going to tell us today, and he will introduce us to this nice survey that he has done.
Okay, thanks. Thanks for having me. I like coming back here because I'm from here. And I have a tendency to not speak very loudly, so it's the job of the people in the back to remind me to speak louder. All right, thank you. Cool, so I'm going to be talking about Herschel surveys as opposed to Herschel observations of individual galaxies at high redshift, which are really awesome. But that's not what I'm here for. I'm here to talk about how you can use the survey as a tool to get at interesting stuff. Okay? Here's the outline of the talk. What is this cosmic infrared background that is the jargon that only 5 people in the world actually use? What can you do with auto and cross correlations of the CIB as a tool for doing things like studying clustering of star-forming galaxies and making the connection between the optical galaxies, which astronomers are more familiar with, and these infrared background? And then using this knowledge towards studies of galaxy evolution and cosmology. And then I'm going to talk about HERS, the survey that Amir was introducing, but it's going to come at the end after a whirlwind of information. So I'll save all the pretty slides for the end. Okay, so I've learned the hard way that you have to tell people what it is you're talking about. What is the infrared background, and what is the infrared part of galaxies? Why should we even care? Here's a pretty galaxy. This is the Andromeda Galaxy M31 in the optical and in the infrared. The infrared being made up of far infrared and submillimeter. It's a composite. Both of these are color images, right? But notice that the light here is happening in the center, more or less. There's this satellite galaxy here. And then the light here is really coming from these arms. Well, what you're looking at in the optical is starlight. And what you're looking at in the infrared is dust light. Dust light because the dust was warmed up by starlight. See what I mean? So, and also keep in mind that most efficient at heating this dust is very energetic light. Things, UV light, the kind of light that comes from young hot stars, the kinds of young hot stars that are found in star-forming regions. So not only is this showing you the light that you couldn't otherwise see because it got absorbed, but it's tracing the star-forming regions in these galaxies. So dust is a tracer of star formation in galaxies. Okay. This is a spectral energy distribution.
So, what was the date that allowed that great picture of Andromeda? No, this one, the infrared.
When was this?
No, what was the date it is?
Oh, this is Pax Inspire.
Pax Inspire, right. And I'm a little surprised that there's no visibility to the central part of 31.
Well, that's the thing, right? I mean, there's not really much star formation happening. These are old stars, and they're not really heating the dust. Does that mean that dust doesn't exist?
No, but I'm thinking, what would it be like in the center of our Milky Way?
Well, definitely when you look into the center of the Milky Way, say CMB, you see stuff. But I'm not really sure that that is the center, I think. You're looking through a bunch of arms.
No, but there's action in the center of our galaxy.
Yeah.
And there's a molecular ring or something around it, which is
I don't know what it looks like in the Milky Way, to be honest. But it's also possible that it is dust, but it's much hotter, and so it wouldn't peak in the same ways that this would peak at 250 microns.
In other words, there's
Yeah.
compression that's going on.
Okay, so this is the spectral energy distribution, meaning how much light is coming out at every wavelength. This is the part of that SED here in the optical and UV, near infrared. And this is that bump coming from dust. So the optical light was absorbed by the dust and re-emitted as a modified black body, approximately as a black body. And then the ratio of this bump between the optical and the infrared is an indication of just how much star formation is actually taking place. So these really messy things that astronomers like to call Eulergs really have a lot of their luminosity coming from dust. Whereas old elliptical galaxies, these red and dead guys, there is going to be some dust emission, but it's certainly not the dominating factor. So now we know that the infrared background, it absorbs the light. And it's a tracer of not just star formation, but when you look in the sky and you see the infrared, you're mostly seeing these dusty star-forming galaxies. So it's a tracer of star formation throughout the universe's history, and I'll get into that a little bit more. But this is one that us CIB people love to show. It's a measurement of the intensity of the background at all these different wavelengths. And the takeaway message here is that the optical and the infrared are more or less the same amount of energy is coming out. So about half of the light that's come out of stars has been absorbed by dust and then re-emitted. So it's actually kind of important that we understand the infrared background like we understand the optical background if we want to get a full picture of galaxy evolution. It's fair enough. So why does the infrared, why does submillimeter seem so new, right? If we have a plot, and here we have it, year versus the area of a survey divided by the depth of the survey. This Hughes 98 submillimeter galaxy, Nature paper, very famous. And then in the next 10, 5, 6, 7 years, we had a little bit more progress from SCUBA at 850 microns and 450 microns, some Loboka. Then here in Toronto, or one of the people, we built BLAST, and this was my PhD project. And that made some progress. And then Herschel and Planck arrived, and boom, right? It went crazy. So I'm here to talk about a little bit of BLAST, but mostly about Herschel. These surveys here, Hermes and HERS. But before I get into that, to answer the question, why did this explosion happen and why did it happen so dramatically, it's because the submillimeter is difficult to observe, particularly from the ground. This is a transmission, so this is wavelengths are going this way now, frequencies this way. The red is where the sky is transparent to the infrared light, and this is where it's opaque. So the telescopes, the first telescopes that were successful, SCUBA at 850 microns, Mambo and Aztec, they were trying to exploit these regions here where the air was transmissive, right? But these opaque bands were less successful. Now, BLAST and SPIRE, they wanted to observe at 250, 350, and 500 microns, and to do it from the ground is challenging. But to do it from not the ground, that's another thing, right? So this is that same plot that I just showed you, and this is from a mountaintop, from an airplane, or from a balloon. And so notice that, of course, it's becoming much more transmissive as you get from a balloon, and if you can do it, you go to space. So that's what happened. We went to space with SPIRE. Well, there was a few instruments on Herschel, but I'll be talking about SPIRE, which were at 250, 350, and 500 microns. This is a 3-color image. The SPIRE instrument was similar to the one that was used on BLAST. But the takeaway I want you to have here, particularly if you're an optical astronomer, is that the beam sizes were quite big, even for SPIRE, between 1/4 and a half an arc minute. These are the 3 spire bands next to the SED of dust. And what's happened here is this is the rest frame dust SED in black. And as it redshifts, it gets fainter, right? As something gets farther away, it gets fainter. But what's happening is this peak is shifting into these 3 bands here. So it wasn't an accident that these 3 bands were chosen to bracket the peak of this dust SED at high redshift. This goes by the jargon, the negative K correction. You can show it in a different way. You can show the flux density versus redshift. At 70 microns, as you would expect, as something gets farther away, its flux density plummets. But in the sub-millimeter bands, as you get farther away, it's not becoming dimmer quite as fast. And even at 1 millimeter, it's actually turning up, so that the same SED looks brighter farther away than it does locally. And this is that negative correction taking place. So what it means is that you have sensitivity to high redshift in the sub-millimeter. And that sensitivity increases as you go to longer wavelengths. And you can use that, and I'm going to show you how you can use that later. If you're interested in the star formation history of the universe, this is been shown by many people. This is a model from Baruzzi et al. And you want to measure it in the optical. This is the data that you collect before you correct it for obscuration. This is what happens after you correct it for obscuration. And this correction is quite dramatic. And what isn't shown in the error bars here is that this is a systematic as well as a statistical error, right? Because getting this correction right from the local obscuration, from their local obscuration, right? And whether or not there is a dependency on redshift for this correction, and really how much you should believe because of selection effects, because some of these things are so dusty at high redshift. Now, we don't have that problem in the infrared because we are tracers of star formation, and we don't have to worry about dust getting in the way of light because we're looking at the dust, right? So burn this image into your brain because we're going to come back to it. I'm going to be talking about, for the first bit anyway, results from Hermes. Hermes is a survey, and this confuses people, so I've learned to say surveys. Hermes is a survey composed of surveys. There are many surveys in Hermes, and it's a wedding cake style so that some of them are very small and very deep, and some of them are very wide and very shallow. It's a huge team. This is me. This is Joaquin Viero. He's a colleague of mine, and sometimes I get invited to conferences, and it doesn't really make any sense. And then I'm like, oh, I think you meant him. So you can continue to invite me, but be sure. Okay, this is great. We can do a lot of things with the submillimeter, but of course that it's not all roses, right? And the reason is this source confusion. This is image from the Hubble Deep Field from the Hubble Space Telescope, 1 arc minute by 1 arc minute. You can see a lot of galaxies, and it's very impressive. This is the same image from Herschel Spire at 250 microns. This is our best resolution in the Spire bands. And just to convince you that I'm not pulling your leg, you can see that they're tracing the same places, right? So here's contours of the 250 microns on top of this optical image. And I think it's fair to say that there are many sources contributing to this. It's not necessarily true. It might be that one of these things is dominating all of the flux in that submillimeter. It's hard to tell. This is what we call source confusion, but there's other ways that you can show it. This is the noise in the map versus the integration time. As you integrate longer, you expect the noise in the map to go down. That's this red line here. As you integrate longer, the noise in the map, the RMS of the map goes down. But what happens with source confusion is you integrate longer, you asymptote to this line, this confusion limit. And that's why we call it the confusion limit. If you want to see it in pictures, this is one of the shallowest fields from Hermes at 4 scans. This is by far the deepest field from Hermes. Much more data. You can't tell by eye that this is all that much deeper, that you're getting all that many more sources out of it. Okay. This is a submillimeter map. The colors are a bit nicer on my screen. But what I've done is I've stretched the colors so that the green is these ridges of faint emission, and blue are these are the valleys in between this faint emission. And now I've taken a catalog from the optical and drawn a circle on each of the sources in that catalog. And I think it's not unfair to say that most of these sources are falling along these ridges of faint emission. So there's definitely information in these maps, even if we're not necessarily resolving the sources themselves. And now I want to talk about how we can get at that information. And I'm going to start with clustering, and then I'm going to go into something else, stacking, different ways to get at this data. Okay, long introduction, but I think that the submillimeter needs it because it's a new enough field that people aren't really that comfortable with it yet. So I want to measure clustering. And clustering, how it's typically measured is you identify your sources. Some are red and some are blue. And some of you have seen this slide before. But different galaxies, they cluster in different ways. And the way that you typically measure that is you measure the distance between the galaxies. You compare that to random. And then you plot it either as a power law, or if you want to get fancy, you plot it as you model it with a halo model. But the point is that it's fit more or less well by a power law with these red galaxies, which trace larger structures, more clustered than these star-forming galaxies. But we can't do that because we can't identify these objects, right? So what do we do instead? Well, I had the luxury of coming from a CMB group, right, who built this. It's great. They built this astronomy experiment, took this beautiful data, and then said, well, what do we do with it? Well, we're CMB people. Let's take its power spectrum, right? It turns out that the power spectrum is a good thing to do because, like we've already seen, these bumps and ridges, right, they're coming from galaxies. So if you take the power spectrum, it ends up looking like this. It's made up of 3 dominant components: the Poisson term, which is the fact that you're discretely sampling the background. It's shot noise. This 2 halo term, this linearly biased dark matter. And then this extra term, the 1 halo term, the non-linearly biased dark matter. The fact that multiple galaxies are sitting in these very massive dark matter halos. So this nonlinear term is providing some extra power on small angular scales, which makes having that extra resolution from what you might have from other full sky surveys actually quite important. So keep that in mind as well because we're going to get into that later. Here it is. This is the power spectrum in every band, 250, 350, and 500 microns. This is the cross-frequency power spectrum, 250 and 350, and so on. These different colors, I'll explain. Zooming into the 250 micron power spectrum, you see that I have these different numbers here. These represent the flux cut. And let me explain. So remember before I showed you that the red galaxies and the blue galaxies, they cluster differently. And then if you were to take the red galaxies and cut them into things that were more massive or more luminous, then those things would cluster differently as well. More massive things would cluster more. But I don't have that luxury because I don't know where the sources are. So what I do instead is I chop off the bright things, right? I mask out everything that I can resolve, slice after slice, and see what it does to the power spectrum. And it turns out that it does quite a lot. It doesn't do much to the 1 halo term, this linearly biased dark matter, but it does a heck of a lot to the 2 halo term. So as I'm masking out sources, if they're sitting in these large dark matter halos, I would expect the 1 halo term to go down, and it seems clearly that it does. What do you do when you have this great data? You try and fit it with a model. And now forgive me if I'm going to go really quickly over this, because this is a talk in itself. You might have even heard Guylaine Lagache give a talk like this, and there's lots of details. It's really interesting, but I'm going to basically brush right over it. But the point is that the halo model that we used was an extension of this Shang et al. Model, and its point was that it tied the luminosities and the masses of the dark matter halos hosting those galaxies together. And it did it with a log normal relationship so that there is a peak halo mass for efficient star formation. Okay, and then we did it with a couple of different SEDs, dust SEDs to describe the sources so that we know what the difference is in the flux between this band, and this band. We had to model it, so we first started with a single model. We added a single dust component, no evolution in Redshift. Then we added a double component, a warm component and a cold component, and we let those vary. And then we did that with and without the Redshift evolution. And key to this work, which I think it's become standard now, is that we fit the auto spectra and the cross spectra and the number counts. We fit it all together. So that the fact that these different bands are sensitive to different redshifts because of that negative K correction, the cross frequency spectrum is sensitive to the overlap between these sources. There's a lot of information there, and it's actually pretty easy to fit one panel, but it becomes extremely harder to fit them all at the same time. So there's a lot of power here.
So let's go back. Okay, so the double component, did you fix the temperature or did you let that vary?
The temperatures were allowed to vary.
And in bands or with every single object?
No, it's
How did you do
still
it?
simple, right? I mean, there's an evolution.
So what does that mean? You allowed it to vary at T of Z?
T of T, yeah, 1 plus, or T to, yeah, 1 plus Z to some beta, to some alpha.
And what were the sort of average values? Were you up to 50K for the dust, or were you pushing down to 30? Did you have a 17? What did you do?
Well, if it does vary with Redshift, I'm going to show you a really awesome slide later.
It's going to reveal that information?
Yeah, but actually I didn't. I took it out because of time, but I'll put it back in.
I know,
When we
but
get
this is
to
what
it,
we
I'm going
want
to
to
put
know
it back
about.
in because it's kind of cool. Yeah, I'm going to put it back in. When we get to it, I'm going to stop this. I'm going to put it back in because it's kind of awesome. But yeah, the temperature varies from low redshift to high redshift. There's a very clear gradient, but you can't see it here. You see it in the stacking. So when we get to the stacking, I'll show you.
Well, all right, let me say this just another way. So at great expense with Planck, we have a very good model of dust in the galaxy, including some aspects of temperature, but with that stupid beta model, but let's not get into that for the moment. 17K, but with some variations. So take that to Redshift 3. How important is such a component, or is that swamped by fitting to other things when you only have 2 components, or worse yet, 1 component?
I don't know that we ever did try fixing it at 17 degrees.
Well, I'm just saying, you know, ARC 220, you would do like 30K or something.
Right.
And so, and they would be sort of more dominant.
Right.
And so the question is, are you eradicating the Milky Way, poor Milky Way, when it's at Redshift 2?
That is what is preferred, yeah.
You're getting rid of it.
If you pick
It
one
doesn't
temperature, it tends to not look like the
That's
Milky Way.
because the precision isn't good enough.
I don't know if that's it.
Well, it's got to be.
When we see the stacking, we can see again if that is the case.
There's probably just selection with the stacking.
You might be
Anyway,
right.
I will have many more questions about this, but that was that's
Sure.
the main one, because I had these double components in back in the 90s when we were first dealing with scuba.
Yeah.
And as I described to Amir and company, this is really
these are the 3 different models, and the chi-squared of all of them is basically the same. Right? So we don't disagree. These models are great until they're not great. So those are the 3 models that I described. The chi-squareds are good, but they're good for all of them. And so we don't really have the power to tell the difference between these different guys. One thing we do find is that all of the models prefer that peak halo mass was 10 to the 12.2, which is very similar to what other people are measuring and what other people are finding with models. So here's just one example. This is from Baruzzi et al. He's got this model where the peak is at 12.2, I think, right on the money. And that the evolution with Redshift, it doesn't seem to evolve with Redshift at all. I mean, a little bit, but it's pretty constant with Redshift.
But that depends where you make the boundary between what you call a 2 and what you call a 1. I mean, if I shift that boundary, then I will have changed that number.
Well, maybe that's the case. But I can't speak about this too much because I still don't really understand it fully, to be honest.
So the 3 models are single temperature, double temperature. What is the third one?
The third one is with and without redshift evolution. So in fact, there's 4 models, but we didn't use one of them because it ended up being identical, so in every way. Okay, these are slides now. These are slides that I'm about to put in that I think was going to compromise the length of the talk, so I'm actually going to jump them because I see that I'm going slowly. But except I'm going to touch on them and then we can talk about them later. But this is the ACT power spectrum at 150 gigahertz and 220 gigahertz. So at 1.4 millimeters and 2 millimeters. And this is their cross-frequency spectrum. Notice the bumps and wiggles that you're all used to seeing when you see a power spectrum of the CMB, and then they do this, right? This is a combination of shot noise and clustering. The reason it doesn't look flat like it did before is because the CMB tends to, well, I don't have to tell you guys, but the CMB tends to plot in L squared CL because this is so steep that you have a better way to see this curve. Yeah, I'm really going to skip this stuff, so forgive me. But the SZ effect, I say I'm going to skip it and then I'm going to skip it. The SZ effect is the CMB going through these halos that have lots of hot gas in them, and then the CMB gets shifted, and then it appears as a dark spot in the CMB, as opposed to a galaxy that would, a very bright radio galaxy or whatever, that would appear as a bright spot in the CMB. And if you're interested in these guys here, the SZ power, which is buried below all of this stuff, you better have a good model, a good understanding of this foreground. Okay, now I'm skipping Freon, I'm sorry. But no, I'm not. But it's cool, right? The SZ effect is a combination, actually, of the kinetic SZ and the thermal SZ. And if you want to go after this kinetic SZ because you're interested in probing reionization, then already it's sort of difficult to separate those 2 components. But then you have another problem, is that the thermal SZ is also correlated with the CIB. Because, as we've already seen, infrared galaxies tend to live in these massive clusters. Right? And that's also the source of this thermal SZ. So if you don't have that problem, already separating the kinetic SZ from the thermal SZ is hardish, right? But if you add that uncertainty, then separating these 2 is a nightmare. I'm going to keep going. Well, we're making progress on solving this problem by asking the question, what is the contribution to from the CIB to the CMB by doing a cross-frequency analysis between these 2 different maps? So we did this already, actually, here in-house, between BLAST and ACT. And done, Amir and I, in 2011, and then the ACT collaboration as well, of course. And that's these green points. And really recently, I mean, in this past month, Planck put out their cross-frequency analysis between their CMB channels and their CIB channels, and they got these guys. So look how complementary, right? Not only did they agree, which is great, but they get the one halo term, they nail the one halo term, and we get that two halo term. And if you don't have this, then there's a bit of a degeneracy. Well, there's a lot of a degeneracy between this two halo term and this flat term. So this is definitely providing some very valuable things. So Planck has error bars of like nothing, right? But having the ability to bracket the rest of that power spectrum is really great. And pretty soon, we're going to get some even more exciting results from ACT and Hermes and HERS, which I'm going to describe later, as well as SPT has their own Herschel field, and they're doing the same thing. So these error bars are going to start to match these error bars, and we're going to have a lot of power for these models. Okay, other things that are cool that you can do, and I'm really going to skip, but the CMB is lensed, right? And the CMB is lensed by dark matter. Dark matter, remember, that's what hosts the CIB. So if you do a cross-frequency spectrum between the CMB lensing and the CIB, which is this 253, 15, 500 microns, and you filter it appropriately so that you're looking at the same angular scales, this is that lensing map, and then these contours are pasted onto the CIB map. And you can see by eye that there's a correlation. That's pretty cool. This is the cross-frequency. I'm going fast on purpose. And this is the same thing that Planck ended up doing not long afterwards, and they totally nailed it. It's kind of awesome. But this bias, the uncertainty in this bias was not uncertainty in the measurement, which was great, but it was the uncertainty in the redshift distribution of the infrared background, which was one of the things that we already found was a degenerate parameter with the temperature templates from before. The takeaway from the clustering is that the dusty star-forming galaxies, they trace the dark matter distribution. If you only remember that, right? And that the most efficient halo mass for hosting these dusty star-forming galaxies is 10 to the 12.2. But that the redshift distribution depends on the wavelength. More massive halos seem to host more luminous dusty star-forming galaxies, and subsequently this TSE-CIB correlation complicates estimates of the kinetic SZ signal, which you would like to know for inflation.
So can you go back to the previous slide?
Yeah.
So that's Planck, and then the other one is.
Yeah. Okay, but I want to do the stacking because I'm very excited about it.
Before you do the stacking, I'm afraid I'm going to stop you for a second.
Okay.
So let's
Here?
go back. No, one more.
This.
No, that one.
Yeah.
Okay, so the problem that I always had, and one of the reasons for not being that enthusiastic about the halo model, is that you can't really do an infrared luminosity correspondence to halo mass because what bursts up depends upon interaction. And that is not well taken into account to this day by anybody.
No, that's right.
But it's the big problem. And so that statement where when it's doing some kind of abundance matching is just, a fancy. Unless you can point to strong evidence that that's true. I mean, it's true for some population.
Yeah.
Because, the things in the center of the cluster,
Right.
when they're bursting, that's going to be a big deal. But then there are the other things that can be in less extreme environments, but
Right.
they just happen to have an encounter that causes the gas to
Well, so now let's imagine that we can identify what these things that might possibly have an encounter. They might end up being unresolved in the infrared, and so making that connection with. So just say in the optical, you go in the optical and you see these galaxies and they look like they're mergers or whatever, and you have a statistical way to separate these things that are obviously mergers from things that are obviously quiescently sparkling.
No, but even that's not the case, because you don't actually need it to be a merge. It can be a perturbation that causes the gas, which is hung outside, to then pour into the center and cause a starburst.
Yeah. No, but, I mean, I don't have the answer how you do it.
But that's the valve, the control valve that does not exist on any of these models. And my view used to be, and I would be very happy to be demonstrated to be wrong, is that that was a very important component here, which was like a random variable being thrown into the whole process of trying to relate observations to theory.
No, I think you're right. And I think that, that there's two things that have to take place. One is we have to identify the spatial distribution of that stuff so that we can put it statistically into the Halo model. But first we have to figure out how to even ask the question. And I think that might actually be the challenge.
Well, then in the Milky Way, what's the efficiency of conversion of ordinary starlight to infrared?
What's the what?
You were touting 17 degrees.
Oh, no, but the Milky Way, from this point of view, is, I mean, I don't disagree with that, is a bit irrelevant. It's basically where you're actually making a little starburst, but the starburst is occurring not because it's a very massive halo, but because there's been a disturbance which has caused dust, which wasn't converting, suddenly convert into a big burst of star formation, right? An episodic thing, right? That's basically the thing that, at least for a while, everybody was leaning towards that being the fundamental paradigm with a mass relation, but not that much of a mass relation. And then, I think partly by exhaustion, they went away from it because they so much wanted the Halo model to work. I mean, it's like, because we can't do the other one, let us enforce the Halo model on the data, which is a mass-related issue.
I think you're right, but I have a feeling that it's now starting to open up.
I hope so,
Yeah.
because the data is great.
Well, I'm certainly pushing that way. And this stacking, I think, is sort of the key.
Well, there's just an elementary point, isn't it, I assume this to you, that the integral starlight is dominated by lower mass stars.
Yeah.
But if the conversion efficiency is small enough, or if you have a certain flux threshold, so you are biased toward brighter things like
Yes.
this, your volume is bigger. And so those two things combined win out.
It sort of goes like T dust to the fifth or more. And so, and you can get sort of 30-degree dust that makes a really big deal relative to 17-degree dust. And then if you can get 50-degree dust, which you can do in the central regions, then that's a really big, exciting, and that wouldn't be in this model.
Making it longer instead of shorter. Yeah. That's okay. This is exciting stuff. Okay. So now we get onto stacking, or in other words, cross correlations with ancillary catalogs. Okay. Remember, I showed you this before, that the sources trace the infrared light. What you would typically do if you wanted to know what the flux of the source was in a background that was unresolved is you would take each of those circles and you would cut out a thumbnail. And then you would take each of those thumbnails, you see what this is? This is a thumbnail around each of those sources when there's nothing in it, right? But then when you average them together, what comes out of the nothing, what comes out of the noise is these sources. Now I'm going to stress on this point here. The key to why this even works in the first place is that if you have no clustering, which is fiction, right? This stuff doesn't exist. But if you had no clustering, you had no correlations, then the fact that these sources are overlapping, I'm doing this backwards, but the fact that these sources are overlapping will not bias the result. And this I show by showing the stacked input versus the stacked output over the stacked input. And one means that you're unbiased. And as a function, the color here of the full width half maximum of your beam. Remember, our beam at the best, in the best case, is this yellow here, 15 arc seconds. In the right? So I did the slides backwards. What I meant to do was show you this first. These galaxies, if they are clustered, when you convolve them with the beam and then you cut out a thumbnail and you average these things together, you're double counting for the fact that it's simple, right? The fact that you're double counting that flux. But there's a way around that. It's actually quite simple. So if this sounds complicated, you think it's harder than it is, right? This is really simple. You take the fact that your map has sources in it, but when I showed you the map before, you saw blobs, right? It had a shape. Now, if you can reconstruct that shape with a catalog, then convolve it so that you have the same beam, and then regress it so that you can match the shape. What you can do is that you can measure the average flux of the sources in your catalog. Right? So if you want to know the flux of every single guy, you can't do that. It's unresolved. You could do it with almost, but good luck getting time. But you can do it if you have a catalog with thousands of galaxies. If you decide, I'm going to split this catalog into things that are similar, and I'm going to ask, what's the average properties of the galaxies that I think are similar? So this takes into account the fact that these galaxies might be clustered. If you do it simultaneously, so you split it up into things that are different masses, then you can get the average properties of things that are at different masses. Or if you take, just say you take things that you figured out in the optical seem to be some sort of perturbation. I don't know exactly how you do it, but if you could, something that you think is indicative of a starburst in the optical, and something that's indicative of a very normal guy then you could stack those simultaneously. You could get the average properties of those. So you can slice it up however you want, and you can get the average properties of that sub-catalog. The key here is that you have to be complete, because you want to account for all of the flux. If you're not accounting for some flux, right? If there are some sources that you're not accounting for, then this isn't going to work, because that is going to provide some extra flux that you're not accounting for. I hope that makes sense. This is a simulation to show that it actually works. Again, stacked output versus input. One means that it's unbiased. This is a simulation with clustering in it now. So the bigger the beam, the more the density of the sources on the map, the more your bias goes up. If you do it with this simultaneous stacking technique, you can see that it really works. Of course, again with the caveat that you're complete. Here it is in data. This is some catalogs that I put together and then convolve them with the beam. And this is the map that I'm trying to regress it with. Okay, so here it is. Here's the result. We use the catalog from the UDS, 2/3 of a square degree. We have optical and near infrared, and we select by K-band magnitude. So we're doing basically a mass selection. We have 80,000 sources in this 2/3 of a square degree. We measure photometric redshifts, not spectroscopic, because it's a huge catalog, and masses with FAST. We do them both with SED fitting. And then we stack them not only on Spire, but we're stacking from Spitzer at 24 microns all the way to 1.1 millimeters with Aztec. This is the result of the stacking as a function of redshift on the x-axis and flux density on the y, and we split it in mass. And we also split it in redshift and we split it in mass. And the key to remember is that if they're uncorrelated, they don't bias each other. So what we do is that we stack one redshift bin at a time, because something at redshift 2 doesn't know anything about something at redshift 4. So I don't have to worry about that biasing my result. And that's why I can get away with this. That's why I can stack 80,000 sources at the same time. So here's the flux density. Notice that the more massive things are brighter. As you go on with redshift, they get fainter, as you would expect. It's getting farther away. That's not so much true anymore at 350 microns. We still have this trend where the more massive things tend to be brighter in the infrared. But the drop-off with redshift isn't so dramatic anymore. And by the time you get to 1 millimeter, you get negative K correction, plus the fact that things are more luminous for the same mass at higher redshift.
What's the Aztec beam?
It's 30 arc seconds. No, it's not. It is 25 arc seconds. From
And so what are the fatal points? You have two primary circles.
That's right. So the open circles are for complete bins, and the closed circles are for incomplete bins. So as you get to lower mass, higher redshift, your catalog is starting to become incomplete.
And does SIMSTACK was the name of the code? Do you assume any particular form of clustering quantities or?
No, I don't have to, right? That's the whole point of this. I don't have to use a halo model or any kind of assumption of clustering. I just use the data. The data has the clustering built in. Okay, so this is the same thing that I showed you before, but now for every single point. And if I take any one bin in a mass and redshift, I can fit it with a very simple dust SED. And then I can do that for every single bin. So now for every mass, stellar mass, and redshift, I have a dust SED. And the point of this paper was to ask the question, how much of the infrared background can I explain with optical galaxies? How much of the infrared background is coming from things that I already know to exist in the optical and the infrared? And it turned out that the answer was approximately 80%. And if I split it up into redshift bins, the lower redshift are providing more data, more information or more flux at the lower wavelengths. And as you step to higher redshifts, you're contributing more and more to the longer wavelengths. Right? So we're seeing a negative big correction again. If I split it up into mass bins instead of redshift bins, I notice that the most luminous guys are actually not the ones contributing the most. It's these mid-mass ones. The ones that have they have flux and numbers in them to their advantage. So most of that CIB is coming from these mid-mass galaxies. And then if I do the integral of the infrared, if I do the integral of the dust SED, I can estimate the infrared luminosity. And if I plot that as a function of mass, color, and redshift, I notice that the luminosity is increasing with mass to higher redshift. And then we have to take this with a grain of salt because of incompleteness. But it seems like we have this turnover taking place for lower mass stuff. So having more deeper data is going to help us solve this problem. And then there's this other thing here, which is really cool, which is really weird, which I can't explain, is that presumably quiescent galaxies, red and dead galaxies, that we identify in the color plane, U minus V, V minus J. As you go to higher redshift, they seem to really be contributing a lot of, or not contributing a lot, but they seem to really be lighting up. By the time you get to past redshift 2 or 3, they're almost as luminous as their star-forming counterparts. How could you explain that? You could instantly think, well, that's obviously a mistake. Your U minus V, V minus J, as you go to higher redshift, that color becomes much less reliable, and that's true. There's no doubt about it. But what's weird about it is that because this is an average, for your colors to be wrong, they have to all be wrong, right? And if they're not all wrong, then if 1 in 10 is wrong, then that 1 in 10 has to be so much brighter than the other things. It has to be 10 times brighter, right? So it's not clear what is the origin of this. And it's not just us that has seen this, right? We did this with BLAST a couple of years ago. We saw the high redshift massive quiescent galaxies had some sort of emission coming from it. It's been shown recently from Fuma Valley. They only got up to redshift 2, but they got the same answer. Marchesini, that's how you pronounce it. Marchesini. So this is something that has been seen, but I don't think anyone's ever asked a question to this redshift. So it's a work in progress. Then you can split it up by luminosity class. it's not that exciting to split it up by luminosity class, except to find that Galaxy model from 2 years ago seemed to have predicted this already. The Bethlehem and all model seemed to have predicted this already, and we seem to disagree with the Bethlehem and all model for the Eulers. For the most luminous, the brightest, these dusty starbursts, the ones that we've already heard might be the problem that is causing us headaches. And that's just because these really dusty starbursts might not actually show up in our optical catalogs because they're so dusty. And there are examples of that too. The Dale paper, they found some supermassive galaxy, and when they looked at it in Hubble, and it was still never would have made our cut. So they definitely exist, but it looks like maybe a lot exists. And then, tying it back to the infrared luminosity density from before, we see that we can reproduce that curve pretty well. The pink are the totals of all these different curves again. And that at low redshifts, it's these lower mass guys that seem to be providing most of that infrared luminosity. And when you get to higher redshifts, most of that is, well, a large part of it is coming from these really massive guys. So even though they don't really provide that much, it's like of order of 5% to the total CIB, they're really contributing quite a lot past redshift 2. So we've seen this before, this is downsizing, right? But it's interesting to see it now in the infrared.
Have you tried cross-correlating these subcomponents with AGN?
AGN is also something that we've tried, and AGN does seem to account for some of it. I'm going to show you another thing, and then we can talk about AGN. This is the temperature one that I took out because it was going to end up taking a lot of time, and we've probably already gone over it. So you can stop me wherever you want. But this is cool. This is the rest frame temperature versus redshift. And if you think it's a selection effect, well, these catalogs are complete, at least for redshift 2, for basically all masses. So, and we see this evolution of temperature for the dust SED model for our stacked fluxes. And it's pretty clear. And this this goes as temperature times Z to the ET, which ends up being something like 0.4. And then, if you in resolved studies, there's always this talk about this luminosity, temperature luminosity relationship. As the luminosity goes up, the temperature goes up. But that I argue is a selection effect, because if you look at the mass versus temperature, we know that when the mass goes up, the luminosity goes up. I already showed that with the stacking. But here, when you look at one redshift slice and you look at the mass going up, the temperature actually seems to, well, the error bars, if you can believe it or not, it's either staying level or actually even falling a little bit. And then another thing that we said before was degenerate, was the redshift distribution of the infrared background. Now we have a very good measurement for at least 80% of that stuff, because it's still a lower limit.
Did you do that exercise with the 2 TD model, or is that just 1 TD drawn out?
I did not do 2 TD, no.
So there's no indication of there being an extra bump.
I think we might actually be able to do a 2 TD for the really high signal to noise, but I would be nervous because I didn't even fit anything you want at that point. Yeah, I don't know. It's a good question. Okay, so the takeaway from stacking, because I already gone over time, so I'm not going to get into hers, it's too bad. But the takeaway from stacking is that the mass-selected sources make up about 80% of the CIB, and that the mid-mass galaxies are responsible for most of the infrared background, but that high-mass galaxies seem to make up most of the luminosity. Most is the wrong word. A lot of the luminosity density at higher redshifts. And there's this puzzling signal from high redshift quiescent galaxies. That this luminosity mass redshift relationship is going to be extremely powerful for a lot of our future AL models and for a lot of models of galaxy evolution in general. I'm just going to show a pretty slide because I promised it to Amir. The point is that to move forward, to get to the star formation rates of these lower mass guys, lot of data. I prove it here, but I'm not going to get into it. And so with that in mind, I PI'd 2 surveys with the idea of put it in a field that's going to have a lot of ancillary data. So this is the Hermes large mode survey, and this is the Herschel Stripe 82 survey. Together, they make up 45 times 3 plus some extra square degrees on the sky. The reason for these funny shapes is that if you look at the sky at 100 microns, you can see that there's a lot of foreground emission. And because that is a serious problem for measuring, say, the 1 halo or the 2 halo term in the power spectrum, but basically it's just really bright. You want to get out of that as best you can. And the Stripe 82 region is not ideal for submillimeter for this reason. So this submillimeter survey covers all of the area that you can get in the Stripe 82 in submillimeter without suffering. The data that exists already and is going to exist, so we have ACT, of course, Sheila and SPIES, which are IRAC warm emissions, HETDEX, which should be starting next year. And this survey here, anyway, the Herschel Stripe 82 survey, has just recently gone public. So if you want to download these maps yourself, made with SIMSTACK, so they're really great, or the catalogs, you can do it from extra.caltech/Herschel. This one I wanted to talk a little bit about because it's similar to some of the great work that Viero has done recently, cross-correlating clusters with ACT. He cross-correlated radio galaxies with ACT. This is something I kind of wanted to show you. This is stacking of quasars. Notice how at low redshift you don't really get much. And then from this redshift range between 2 and 4, actually you get this rise in the stacking signal and then a decrease again. Other things you can do is you can do cluster members and stacking rings, and you can figure out with the infall radius. So if you really want to get into the question of how does the CIB trace the most massive halos, because just say you're interested in just saying that TSZ-CIB correlation, this is something towards that. And so in summary, dusty star forming galaxies, tracers of the dark matter, made up mostly of these typical galaxies that you actually already see in the optical and the infrared. And this is kind of, I don't know about you, but I think this is kind of cool because we never really made the connection between the normal galaxies and the infrared. Thanks.
So that connection of, so you have these optical points, and then it doesn't necessarily mean that emission is coming from that optical point, right? It's just that there's a correlation. So if there is, whatever is doing the submillimeter emission is something that exists that's nearby, correlated, that would then be included as part of that cross-correlation. That doesn't necessarily say that the cause is that optical
but
galaxy.
that would be a really,
Would it?
that would be a scenario, right? Because you're
Well,
going
it's
very deep.
It's actually a reasonable scenario.
But you're going extremely deep in the optical, so and you're picking up basically what you think everything that is all of the mass. So yes, there might be other mass, and it might be that's true in every case. I think it would have to be true in every case. And I think there would.
Why would it have to be true in every case?
Well, because you're going really deep in the optical, extremely deep in the optical. You're picking up basically everything that's there, unless it's invisible.
Yeah, but it's just, you're just doing cross correlations or stacking. I mean, it's not, it's just, saying what does it look like in the neighborhood of this point. It isn't saying that that point is the center of emission.
Sure, that's true. But yeah, well, your pixels, I think, at that point are bigger than even that precision, that level of precision.
Well, a basic question. So the baryonic retention is the infrared efficiency then also be a function of halo mass, and can you get at that? Or,
Yeah.
I mean,
No, absolutely.
yeah.
I think that is one of the things that you're going to be able to do with this data. Right? Once you're convinced that you believe it, I think that it's pretty good.
Did you get star formation rate versus stellar mass? Can you get that out of this? Because you have the
That would have been a lot of citations, but that's not my paper. That's another paper. I breezed over it, but Vinod Arumugan is going to take a similar technique with a similar catalog, the same catalog, and he's going to study the star formation rate and specific star formation rate. He's going to include the radio as well as the UV. So he's going to try and get a real comprehensive look of the whole, of all of this star formation, not just obscured, because this is really just obscured star formation, right? And hopefully back that out and actually get a better conversion from the, this is important, get a better conversion of the infrared luminosity to star formation rate, because we saw with the quasars that there's something going on, that infrared luminosity might not be, that one number that we use to convert to star formation rate might not actually be the right thing to do, particularly the contributions and where they're taking place and the masses of the things that they're taking place are changing.
So, did you use the redshift distribution that you got in the second half of your talk in
That's,
CIB lensing?
no, unfortunately they didn't overlap. So hopefully the next generation of models is going to be able to use this arsenal